Welcome back, everyone, to this theory and intuition discussion on ridge regression, which is the first form of regularization we're going to cover in relation to linear regression. So ridge regression is a regularization technique that works by helping reduce the potential for overfitting to the training data. And it does this by adding in a penalty term to the error that is based on the squared value of the coefficients. And later on, you'll realize that regularization in general has this really common penalty term addition, regardless of how you're actually doing the regularization. For the relevant reading in ISLR that refers to ridge regression, you have to actually jump to section 6.2.1. It's a bit of a leap from chapter 3, since the book doesn't actually cover regularization in general until after discussing more things, but we think it's best to actually cover the relevant regularization techniques for regression right after you learn linear regression. That way, we can still follow along for our machine learning process where we can adjust and tune hyperparameters. And ridge regression has a very direct tunable coefficient parameter that we're going to learn about later. So let's start off by exploring the main concepts behind how ridge regression works. And for this, we're going to need to clarify some notation. Recall that the general formula for the regression line looks like this. You have your predicted y hat, and it's equal to your beta coefficients times your features, x1, x2, and so on, up to, in this case, p features. And then you also have your beta naught, which is your intercept. Now these beta coefficients were solved by minimizing the residual sum of squares. So recall that at the end of the day, we were trying to choose the beta coefficients that minimized this sum of squares, which is just the true y value minus your y hat squared. So we can call this term RSS, residual sum of squares, where you have the residual on the inside, and then you're just squaring it and taking the sum. What we could do is, since I know my y hat regression line formula, I could just substitute that in to this particular notation. So notice here, all I'm doing is I'm taking y hat from RSS and then substituting in my entire beta coefficient just to get it in terms of my coefficients and my features. Still the same thing for RSS. So if I summarize that further, RSS is essentially the following. It's the true y minus beta naught, which is my intercept term, minus the sum of each beta coefficient times each feature, and then that whole thing squared. That's what RSS is, just written in terms of beta coefficients and the feature. So the goal of ridge regression is to help prevent overfitting by adding in an additional penalty term. And that penalty term looks like this, and it's also known as a shrinkage penalty. So let's discuss this penalty term in a little more detail. So ridge regression is seeking to minimize RSS plus the penalty term. Notice here on the left-hand side, I'm no longer calling this whole thing RSS. Instead, I'm just saying it's some other error. So now we're focusing on not just minimizing RSS, but minimizing RSS plus this penalty term. So this shrinkage penalty, what's interesting about it is that it's based off the squared of the coefficients. So in this case, you'll notice that we're actually still dealing with the same set of coefficients that are being multiplied by the features, those b or betas of j, except this time I'm also considering them being squared. And then I'm taking the sum of those squares and I'm multiplying them by some tunable lambda parameter. And we're going to focus in more detail on how to actually calculate that lambda parameter later on. But the main thing to note here is that this shrinkage penalty term is based off not just the beta coefficient, but the beta coefficient squared. The lambda itself will just determine how severe the penalty is. And in theory, it can be any value from 0 to positive infinity. If it is 0, then it simply reverts back to RSS. So if you chose lambda equal to 0, this whole error term just becomes the exact same thing as the residual sum of squares, since you're not considering that shrinkage penalty based off that squared beta coefficient. Let's go ahead and explore a simple thought experiment to get an intuition behind ridge regression. And I often find the best way to understand a lot of these complex formulas is to try to consider the simplest case. And in this case, it would be something like just having one single feature, which means you're really only solving for that beta coefficient times that feature, because the actual shrinkage penalty would only consider beta of j, which is just the single beta coefficient being multiplied by your single feature. So let's imagine the following data set. We have a single feature x and then some target label y. And what we're going to do is split that into a training set and a test set. And recall, with ridge regression, we're trying to make sure we don't overfit the training data. So now we go ahead and just grab the training data. Recall here, my training data points are shown in this pink hue and my test points are shown as blue hue. And when it comes to training, I'm only considering my training points. So eventually what we do is we solve some line that is y hat equal to beta 1 times x plus some intercept beta naught. And regardless of whether we're using RSS or the ridge regression shrinkage penalty error, we're still at the end of the day trying to create a line. And that line, regardless of what error you're actually trying to minimize, will look the same. It's going to be two coefficients, one for the y-intercept and one that is directly related to your feature. So I just want to make that clear that using ridge regression doesn't actually change the formula of the line. It just changes what you are trying to minimize. So again, the only difference would be the actual coefficients found, not the actual formula. So first, let's imagine we're only going to try to minimize RSS. So that's what we've done before. So then you get your fitted line only minimizing RSS. Maybe you do it through ordinary least squares, and you get back your beta 1 coefficient and your beta naught coefficient. However, in this particular case, it appears that you've overfit to the training data. And again, this is a bit of an exaggerated case, but the actual fundamentals will still apply regardless of how many features we have, and also regardless of how we actually do this train test split. The train test split here is just for ease of visualization, but the fundamentals that we're going to cover in just a second will be the same regardless of how you split or how many features you have. So in this particular case, it's quite clear we overfit to the training data. This line, it looks a little too steep as the data starts to kind of have lower y values even as x increases. So what does that actually mean when you overfit to the training data? It means you have high variance instead of a higher bias. So you're essentially fitting to a lot more noise in the training data than actually generalizing to the entire data set. We already know that there's a bias variance trade-off. Regardless of what models you're using, or even maybe what penalties you're using, you will have to trade off bias for variance. So what does that actually mean for ridge regression? Well, the idea behind ridge regression is, can we actually introduce a little more bias in order to significantly reduce variance? So bias variance trade-off doesn't necessarily have to be a one-to-one situation. If we're clever about this, we could, in the best case, introduce a little more bias in order to significantly reduce variance across the entire data set and not overfit to our data. So let's think about this. Would adding the penalty term help generalize with more bias? So adding bias can help generalize this formulation in solving for the beta coefficients. So we can see here we have this blue line that has a little more bias, and the reason we can say it has more bias because you notice it's not fitting as well to the actual red points in the data set. So it's more biased and it's not picking up as much noise or variance. So it's going to get not as good of a fit to the training data, but the idea would be that when it comes to new unseen data, overall it gives you a better fit kind of in the long term. So how does this actually work mathematically? Let's imagine we're trying to reduce the ridge regression error term. And the ridge regression error term is that same RSS plus the shrinkage penalty. And to help with this thought experiment a little further, we're going to consider that lambda is equal to 1. That way, when we're actually, all we're considering here, in this particular case of ridge regression, for the solving of the beta coefficients, recall, this beta 1 is really what we're focused on, that if we assume lambda is equal to 1, then really what we're trying to minimize is the beta coefficient and the beta coefficient squared. So what this actually does in the case of a single feature x is if we're trying to minimize this beta coefficient and the squared of this beta coefficient, then it's going to start punishing it if you have too large of a slope. Does that make sense here? Well, if we think about what a standard line equation looks like, it's y equals mx plus b, where m is your slope. So if we think about our equation, y hat equals beta 1 times x plus beta naught, beta 1 is just the slope of this line. And if you're introducing this shrinkage term, which is trying to minimize this idea of beta squared, that means even small increases in beta 1, again the slope of your line, is going to really start to show up a lot more in this squared term. And then your lambda parameter would just be a tuning factor of how much do you want to punish by beta squared. But regardless of lambda, as long as it's not equal to 0, we're still going to punish those larger slopes. So again, for a single feature, this would actually lower your slope value at the cost of some additional bias, which would show up as error in your training set. But we're going to generalize better to unseen data. To really drive this point home of a single feature in this case, and then your beta coefficient with the shrinkage penalty is actually then kind of lowering the slope and making it less steep, regardless of your train test split, let's think about it this way. Consider that you figured out you're overfitting to the training set. That means if you're overfitting to the training set and you have a single feature x, then an increase in x results in a greater y response. So note here that distance change in x, denoted by that green arrow, would end up significantly increasing with a greater y response. If we add in this shrinkage penalty that in the case of one feature is punishing a large slope value because it's essentially the slope squared that is trying to minimize, then we get this less steep line. So comparing that to the more generalized model that's using the ridge regression error term, notice how much is actually being changed in the y response. So again, if we're looking at that higher sloped red line that's just solving for RSS, you're overfitting to the training data, and that's clear because remember, for a single feature, you have that single beta term, which is the slope of the line. And then if you're punishing the squared slope of the line, realistically, you're going to end up with a smaller slope. And that smaller slope means you're not quickly jumping as far along the y. So this is really the cusp of what ridge regression is trying to do. It's trying to make sure that you're not overly responsive to your training data. That way, when new unknown data comes in, you have a little more biased and you're going to generalize better to new unseen data. So again, that's what happens when you're trying to minimize this additional shrinkage penalty. It's going to punish those larger coefficients, which we can think of as punishing very steep slopes. And obviously, as you get to higher dimensions and more features, it becomes a lot harder to visualize this or even plot it out. But in the case of a single feature, we can hopefully see now that it's quite clear that if you're trying to minimize beta squared and beta j is directly related to a feature, that means you're trying to help minimize the squared of the slope. So you're going to punish something that's really steep, even if it fits well to the training data. So hopefully that leads to less overfitting. Again, in the case of a single feature, that larger beta means a steeper sloped line. And a steeper sloped line would mean more response per increase in x value, unlike if you were trying to minimize that additional shrinkage penalty. Now, we still haven't talked about this lambda term. What about that lambda term? How much should we punish these larger coefficients? I just said that lambda can be anything from 0 up to positive infinity. That's quite a range to choose from. How do we actually choose the best lambda? Well, we can simply use cross-validation. What we'll do is we'll explore multiple lambda options and then just choose the best one based off the performance metrics that we already know about, such as mean absolute error and root mean squared error. In this case, we don't actually have to really do any work for finding lambda. The computer will do it for us. So we can give a range of sensible lambda values and then have the computer start going through them and then start honing in on a zone of the best performing lambda values. Let's explore all of this in Python in the next lecture. I'll see you there.